questions. So recording is starting and everybody knows about it. And I will head over to do a screen share, start broadcast. So ideally this should work now. And can you see the screen? So what we are going to cover today are all the questions and answers. Thank you. Are all the questions and answers that you have asked me in your emails that you want me to cover in this session. As I sent out, I think, when was it? Monday? When I realized that the official teaching session for today has been not found its way into the university timetable, into the student data system. So please put any questions into the chat here. And because this is not an official teaching session, because this is just a question-answer session, there is no Moodle registration. You will be pleased to hear. And that's why I have not put up on the screen the reminder for people to register on Moodle, because there is no Moodle registration. They only set up the Moodle registration when there is an official lecture as stated in the student data system. So any questions, please? Pleasure. Yeah. Although, if there are no questions, then I think it would be pretty dumb of me to upload an empty screen. Okay, so in task 3, what you have been asked in task 3 is actually to calculate the ratios. So to get the ratios of live and dead cells, ratios of cells that are alive, So I just make up some numbers. Let's say we have a total of, let's do something simple here. Let's say we have a total of 30 cells on a plate. And my plates, my Petri dishes, are square. So we've got 30 cells. That's the total. Okay. So we have got 30 cells on the plate, and let's say 10 of these cells are alive. So what we want to find out is we want to see what actually is the ratio of live cells. So one would say, of course, we have 10 over 30. So that would be 0.33 or 33%. And now we would need to figure out, because this is just a sample, what we want to figure out is actually the margin of error. The margin of error for these 33%, because if we did this experiment on another plate, for example, we might find 11 out of 33 cells or something like that, and or 9 out of 40 cells. So if we did this experiment lots and lots and lots, we would probably find something in the region of 33% would be our ratio of live cells. But there would be a sort of a range in which we would find these things, this ratio. And here we've got the lower bound. Here's the lower bound. And here's the upper bound, where we expect this ratio to be located. And what I showed you is actually we can determine a sort of a ratio by hand. And we would do that by basically calculating this ratio, and I call it P here, and this P would be 30 over, oh, sorry, would be 10 over 30. 10 over 30 plus minus a margin of error. And I abbreviate margin of error with MOE. And this margin of error, that gives us basically then what I show here. This is related to this figure here. Yep, that's right, Sabrina. Thank you. So if we look at it, this would be somewhere around 10 over 30 minus the margin of error. And this point here, the upper bound would be 10 over 30 plus the margin of error. Right? That is what our lower and upper bound actually tell us. And that is what this thing here shows. Now, I told you that for, how shall I say, for technical reasons, usually people don't work with this P, and instead they work with what is called the P prime, where we just simply add some people might think it's random numbers, but it just simply works. P prime is just simply 10, what we had, plus 2 divided by 30 plus 4. And these 2 and 4, these are fixed numbers. They don't change, right? And the reason for that is when you are very close to 0, so if you have, for example, 1 cell per 1 cell alive, 1 cell per, let's say, 30 alive, your ratio is very close to 0. P is close to 0. And then the whole calculation totally breaks down. It doesn't work. So therefore, a very famous statistician came up with this idea of why don't we just simply add 2 numbers to that, and these are the number 2 and 4. And they tried lots of combinations with numbers, and they found that when they add this 2 and the 4, 2 to the numerator, 4 to the denominator, then actually the calculations sort of work all right. That is the reason why many programs that you look at add these, what is called the Wald correction numbers. Wald correction. So instead of working with this P, the uncorrected numbers, we work with this P prime or P dash, if you like, and these are the corrected numbers. So what we can do now is we can say, right, we can calculate this margin of error, and we can do it by hand. And I showed you how you do it by hand. So it would be P prime equals, or let me write it differently. What we have is P prime plus minus 1.96. And this is this famous 1.96 number again, which will be revealed in one of the next sessions where this number comes from. But at the moment, just trust me, 1.96 times the square root of P prime, that's this ratio again here, with 12 over 34 times 1 minus P prime divided by the total number of cells, plus 4. And that's basically this part here. This is this 30 plus 4. That would be this part down here. And with that, with this equation, we can actually calculate what this margin of error here, this whole bit here, that's the margin of error, what this margin of error is. Alternatively, if you are too lazy to do so, you use 1.96 all the time. Absolutely. That is the equation. You use 1.96 all the time, although a lot of people just simply use 2, because 1.96, 2, that's pretty close. And it makes it easier on the calculator. Alternatively, what you can do is you use this online calculator, this Evan Miller calculator. And I think I've got it here somewhere. So here is this calculator that I showed you. And you find this under the chi-square test here. Although it's technically not a chi-square test, it is realistically, it is a binomial distribution here that we are looking at. Why the guy put it under chi-squared, I have no idea, but this is where you find it. Okay? So what do we need to put in? We are only dealing with one sample here at the moment. So this is sample 1. Let me see if I can do a markup for that. Okay. So we are just dealing with one sample at the moment because we are just looking at one of these plates. And instead of 14, we said we have 10 cells in our example and a total number of 30. So that is what you put into this online calculator. Yeah? Does that make sense? So that is what it would look like. I don't need to save this. So let's put that in. We had 10 cells, and the program does this Wald correction without you having to worry about anything. So we put in 10 cells alive over 30. And what we get now is this confidence interval that goes from 19.2 to 51.2. So let's remember that 19.2 to 51.2. So for our example, we have lower bound 19.2%, and the upper bound was 51.2%, I think. Is that right? Have I put that right? 51.2, yeah. So all good. So this means our ratio for the true population, if we did this experiment loads and loads of times, the true population ratio in this case is somewhere, we're pretty confident, is somewhere between 0.192 and 51, and sorry, we expressed it as decimal, and 0.512, somewhere in between, right? So that's our lower bound and upper bound. Now, what would be the margin of error be in this case? We've done the lower bound and the upper bound. So what we need to really find in order for the margin of error, we need to find, because this one here is really symmetrical. So we need to find this P prime here. We know that, let me try this properly. We know that this P prime is bang in the middle. This is minus MOE, and this is plus MOE. So all we need to do is we need to figure out, we know that this here is 19.2 and this one is 51.2. So all we need to do is we need to figure out what this margin of error is in this case. And that's not terribly difficult. All we need to do really is we add these together, or we take this difference. Let's do it this way. We take this difference and divide it by 2. So 51.2 minus 19.2, that gives us this point here. That gives us this difference here. What's 59.2 minus 19.2? Anyone? 51.2 minus 19.2. 32, thank you very much. So this whole bit is 32. And what we need to do is take this one. So this would be 32 divided by 2, and that would be 16%, or 0.16. So what we find is that the whole thing is 16%. So this point here, our P prime, would be P prime plus the margin of error. That's the 0.16, gives us 0.512, and minus the margin of error gives us 0.192. So with this simple trick, where we just simply say it's symmetrical, we've got from our calculator, we've got our boundaries here with the 19.2 and 51.2%. We've got the lower bound, 19.2%, the upper bound, 51.2%. We know that our ratio is bang in the middle. Can very easily calculate the margin of error. We just simply take the whole thing, just to repeat, 19.2, 51.2. We take the difference, find the middle, and calculate this bit. And in this case, this is 16%. So this would be the answer for the question, what is the margin of error? If I don't specify, I would just simply, I would go the easy way. I would use the online calculator because life is difficult enough. So there is a decent chance that you make a mistake in the calculation here. So why not use the online calculator? Obviously, if I were to ask you in an exam, where you are in an exam hall, to do the calculation where you don't have access to the online calculator, then you would have to use this equation. But to be perfectly honest, I don't really see a massive point in doing so because that's just memorization. And that does not really do anything to show understanding. Does that make sense? Now, this calculator, of course, also gives us the opportunity to compare that with a second sample here. So if we've got a second sample, for example, with drugs where we have, let's say, just for argument's sake, we have 35 cells, and only 6 cells are alive. Again, we get here for this new sample, let's say that is the sample 2 is with drug here. Then, oops, what happened? That's interesting. Then we get a new bound, confidence bound, or lower and upper bound for the second sample. And now we can also compare these two ratios that we have, or for sample 1 and sample 2. We can compare these two ratios. We would set up a null hypothesis when we want to compare these two samples. And our null hypothesis in this case would be there is no difference between the population ratios and all the differences that we see in the samples is just simply down to sampling error. There's no difference between the population ratios that cannot be explained by sampling error. So all we are dealing with is the sampling error here. And of course, the alternative hypothesis would be there is a difference between the population ratios, and the differences can only be explained with the sampling error, because we always have sampling error, with sampling error and an additional effect, whatever this effect might be. For example, the presence of a drug. What we do is we set sort of a significance level at which point we believe that there is a difference. So the significance level, usually we would set this as 1 minus the confidence interval, 1 minus confidence. So if we say, oh, we want a confidence interval of 95%, which is pretty much standard, our significance level, this alpha, which you sometimes see, would be 1 minus 0.95. So that would be 0.05, which is the same as 5%. So what we do now is then we go back to the calculator, and luckily this calculator does the calculation for us. It gives us this p-value here that you see here with this p 0.13. You see that? P equals 0.13. What does that mean? So we get P equals 0.13. This means we have a 13% chance, 0.13, we have a 13% chance to see these numbers that we got, see these numbers, observe these numbers, 10 over 30, and what was it, 6 over 35 or something like that, to see these numbers if the null hypothesis is true. So we have a 13% chance to find these numbers if we say, well, there is no other effect. What does that mean? Well, we said only if this chance is lower than 5%, then we kick out the null hypothesis. Only if this p-value is smaller than our alpha, 5% here, then we sort of kick out the null hypothesis. And we say we don't believe then in the null hypothesis. In our case, 13% is larger than 5%. So therefore, we say, no, our null hypothesis can stay. If P is low, H naught must go. If P is high, H naught can stay. Where did I write that? It is 1 minus confidence interval. Or in other words, the confidence interval plus this significance level of alpha is always 1. .0, if you like. Does that make sense? So in a way, the steps are always the same. You first set up a null hypothesis and an alternative hypothesis. Second step, define what you want as an alpha, what you want as the significance level. So what do you want as the significance level alpha? 5% is sort of the standard, but it doesn't have to be 5%. You can go for 1%. Or you can go for 10%. Well, that then defines this alpha, that defines then the 95% that defines the confidence level. That defines the confidence level, because if you choose alpha to be just say, let's say 1%, if you choose it to be 1%, what would be your confidence interval? If it is just 1%, what would be your confidence interval? Or confidence level would be 99%. Absolutely right. Yeah, so that would be 99%. And what you would find is that the range in which the population ratio would be larger. We can try to demonstrate that. So what we said here with our samples, so we just look at sample 1 here, where we had 10 live cells in 30 total dead cells. We had this confidence interval from 19.2 to 51.2. Now here we can also, in this program, we can change the confidence level. So let's try to move that to 99%. It allows me to do that. 97, 99%. So I've moved it to 99%, the confidence level. And you see, we had 19.2 earlier. Now it is 16.1 and 56.6. So this confidence level, this interval here, where we think that the true population proportion is now bigger. So the larger the confidence level is, the wider this interval. Okay? But usually we just go for 95%, but we can do it as 94%, whatever we want. We can do it at 83%. And you see, this confidence interval becomes smaller if our confidence level goes down. But as I said, we usually go for 95%. And here are our 19.2 and 51.2%. Are you happy with that? Maybe something interesting to note with the margin of errors here. We said that we have p prime plus minus 1.96, or let me write it like that, plus minus the margin of error. So this means if we look at it, our p prime is in the middle, and here is one margin of error downwards and one margin of error upwards. So it's the same distance with the upper and the lower bound. So here we are lower bound, and here we are upper. So this whole thing is nicely and symmetrical. And that is a feature of the binomial distribution. That it is symmetrical. Unfortunately, if you look at the Poisson distribution for count data, the Poisson distribution, this is not true. It is not symmetrical. That's also the reason why I did not give you the equation for how you do that, and I referred you to the calculator, because calculating a margin of error for a Poisson distribution is a true pain in the backside, and it probably looks a little bit like that. So where you have the count of your cells, so that is the margin of error for the lower side, and this here is the margin of error for the upper side. And you see that these two margin of errors are different. They are all related to the chi-square distribution, but we will talk about probability, what is called probability density functions, and probability mass functions in a different lecture. So I just wanted to mention that here, that for the binomial distribution, it's nice and symmetrical. For the Poisson distribution, this is not true. And you probably noticed that I did not ask you for a margin of error for the count data for the task 2, just simply because it is a pain to calculate these 2 different margin of errors. Whew. Happy with that? Any further questions? No? Well, if there are no further questions, and I think I'm up to date with the group chat. If there are no further questions, I hope you found this question answer session useful. I didn't confuse you too much. We haven't covered the t-test in Excel. So Sabrina, please wait a little bit. The reason why we haven't covered that is because we really need to understand what a t-test actually does and what it doesn't do. And you probably will not be terribly surprised to hear from me that there are a number of different t-tests. And while you probably have done what is considered the standard t-test at school, have you done a standard t-test at school? At A level? In general, not just you, Sabrina, but have you guys done t-test? No, okay. So the issue here with a t-test is you need to really understand in the first place what you are looking for. There are different versions. There are different versions of the t-test, and we will discuss what kind of t-test you are supposed to apply. For those of you who have done them, I bet you have been lied to, as so often in school, because as I said, there are different versions of the t-test, and the version that is taught at school, I would treat this with extreme caution. But we will come to that because that is the thing that you need for task 4. So don't despair. And for those of you who are absolutely desperate to do task 4, the proper way, the proper test here for task 4, and I don't think I tell any secrets, is a modified t-test, which is actually called Welch's test. If you do a bog standard t-test, as some people have done it, there is a good chance that you get just simply random numbers that don't make sense. But I will discuss with you t-test in detail, what it is, what it means. But with these t-tests, we go into an area that we probably need to do a little bit of background research in the first place. So we will do that together. We will explore this topic because we are leaving then the topic of nice count data where we just have some count numbers. We will actually then move into the murky territory of continuous data. But that's a story for another day. Are you happy with that? It's not that I want to fob you off. You will learn it. Oh God, trust me. But we don't have the tools as of yet because we need to do some other understanding first. Any further questions for the last 5 minutes? In this case, thank you very much for watching and participating. And I will hang around for another 5 minutes. If something burning comes up, please let me know. But otherwise, thank you very much. And BI308 will resume next week as per usual. So thank you. Enjoy your afternoon. And those who are doing BI301, I shall see you tomorrow, usual time, usual place with Moodle sign-in. Thank you. Take care. Bye-bye.